Hello. So this are some examples, continuation of examples under lesson 2, the concept of resistance. And we're still under the learning outcomes number 1. So in these examples that we'll be discussing, this will be under the volume resistivity and insulation resistance of cable. So the first example, a piece of copper wire originally has a resistance of 1.20 ohms. The wire is then passed through a series of drawing dies which stretch it and increase its length to 3 times its initial length. Since the volume of copper remains constant during the process, but the wire becomes longer and thinner, determine the new resistance of the wire after it has been stretched. Assume the resistivity of copper remains unchanged throughout the process. So just like we did from our previous example, we identify what formula are we using into this example. We have 3 formulas, and because we have a constant volume, then we can use the volume formula, and also we have the longer and thinner, so the area or the length, and the problem says the length increases to 3 times its initial length. So we can use the length and the volume. So for that formula, R is equal to rho L squared over V. Instead of using the area or the other one, L over A. Because we have constant volume, V1, the initial volume is the same as the other or new volume. And also, the resistivity, it's the same copper. So we have also a constant resistivity. And for the length, it becomes longer. So the length L2 will be, the new length will be increased to 3 times its initial length. So the initial length is L1. So L2 will be 3 times of that initial length. So 3L1. So these are the conditions that we will be using to solve for the new resistance. So dividing again, R2 over R1, and this will be equal to rho 2 L2 over squared all over V2 all over rho 1 L1 squared all over V1. Then the initial value of R, which is R1, is given, and that's 1.2 ohms. So we need to find R2. And we can do that using this equation here. R2 divided by R1, which is 1.2, and we can cancel out rho 2 and rho 1 because they are equal. They will cancel out, and also the volume will cancel out because they are also the same or constant volume. So what remains is L2 squared divided by L1 squared. But we have a relationship between L2 and L1. We know that L2 is just 3 times L1, and we square that and we divide that with another L1 squared, so that we can cancel out again our L1 squared. So the remaining term here will be just 3 squared. So therefore, R2 will be equal to 1.2 times 3 squared. And the answer will be 10.8 ohms. So the new resistance is 10.8 ohms. So that's example number 1. So let's go to number 2. So number 2, a copper wire is initially 1 meter long with a diameter of 2 centimeters. After a drawing process, the resistance of the wire increases to 100 times its original resistance, assuming that the volume of the wire remains constant during the process. Determine the new length of the wire after it has been drawn. Now, in this example, if you look at, there's a given length and there's also a given diameter. So in this example, we can use either log squared all over V, or we can also use the area. Why? Because the diameter is given, and we know that diameter and area is just pi d squared over 4. If this is a circular, because it has diameter. So now, we can choose of the two, but because we used the L squared from the previous example, we can use now the area for this example. So the conditions again, so the initial area 1, is just equal to, or we can just, instead of area, I'll just put it D1 is 2 centimeter. Then what happens to the resistance? The resistance increases to 100 times its original. So R2, the new resistance now, will be 100 times the original resistance, R1. Then, assuming again that the volume is constant, so volume 1 is just equal to volume 2. And we can also assume that it's the same material that we use. It's just copper. So therefore, the resistivity remains also constant. Our rho 1 will be just equal to rho 2. Now, using this formula here, and we divide it again, just like what we did from the previous example, to solve for R2. R2 all over R1 will be equal to rho 2 over V2 all over area 2 squared divided by rho 2 V1 or rho 1 V1 squared all over A, or V1 all over A1 squared. Then from here, we can say that R2 is equal to 100 R1 all over R1, and we can cancel out rho 2 here and rho 1, and we can cancel out again the volume, and we have now just the area. But we know that the area is pi d squared all over 4, so we can put that inside. But if we divide that, if you remember, you divide the area and the area, the pi over 4 will also cancel out. So we don't need to include pi over 4. We can just use the diameter itself. And we can just reverse this. This will become d1 squared divided by d2 squared. d1 squared all over d2 squared. Then, after that, we're given with D1, which is 2 centimeter. So we can cancel out also R1. So we can now solve for the new diameter, D2. So D2 will be equal to D1, which is 2 centimeter. You square that, you divide it with 100. This will be 4 over 100 centimeter. And if you solve for the area is just equal to, the new area will be just equal to pi 4 over 100 squared, or this is square root, sorry, this should be square root, because that's d2 squared, so this will become 2 all over the square root of 100. So 2 all over the square root of 100 divided by 4. So the area now will be just equal to pi over 100 square centimeter. If the problem asks for the area, but here in the problem, it asks for the new length of the wire that it has been drawn. So in case it asked for the new area, you can still do this one using this process. But although it's asking for the length, so if it's asking for the length, then we will use this formula here. And to use that, it's the same process as we did from the previous example. We can just divide R1 and R2. R2 over R1, which is equal to just 100, and this will be equal to we can just use this one here, or no, because it's area. So rho 2 all over rho 1, L2 squared all over V2, L1 squared all over V1. Then cancel out rho 2 and the volume. Then we have just L2 squared divided by L1 squared. And we have given L1, which is 1 meter. L1 is equal to 1 meter. So this is equal to 1. Then L2 will be equal to the square root of 100, or L2 will be just equal to 10 meters. So we can also do that because the length is unknown in the problem. But let me put or also find the new area. So if the problem asks the new area, then that's the process. But if it's just asking for the length, then this is the answer. It's just equal to 10 meters. Next, a 500 meter copper wire with an initial diameter of 8 millimeter has a resistance of 0.015 ohms. After a drawing process, the wire is reduced to a diameter of 3.5 millimeter. If the volume of the wire remains constant, what is its new resistance? So, we'll be using this formula because the diameter is given, but again, the length is also given. It's 500 meter. But we're given also the diameter, which is 8 millimeter, and that diameter will be reduced to 3.5 millimeter. It doesn't include the final value of the length, and we're finding, or we want to find the resistance, so we use that formula. R2 all over R1 is equal to rho 2 L. No, we don't need to use L because we're talking about the diameter, so this should be the area. V2 squared, or V2 all over A2 squared divided by rho 1, V1 divided by A1 squared. Then rho 2 again is the same as rho 1, so we can cancel that out. The volume is also constant, so we can cancel out the volume. And we know that the area is just equal to pi, or proportional to d squared. It's proportional to d squared. Area is proportional to d squared, so we can just put the diameter in the equation. So now R2 is unknown and R1 is 0.015 ohm. 0.15 ohm. So to solve for R2, R2 will be divided by 0.015, and that's the R1. Then we have area 1 squared divided by area 2 squared. But area 1 is proportional to the diameter, which is d1. So d1 squared divided by d2 squared. But d1 and d2 are given. They're both given. d1 is 8 mm. And d2, it's reduced to 3.5 mm. We don't need to convert these diameters in circular mil area, or even in centimeter or whatever, because it will just cancel out as long as the diameter in the numerator is the same unit as the diameter in the denominator. So now d1 is 8 and d2 is just 3.5. So R2, we cross multiply 0.015 multiplied by d1, which is 8, and you divide that with 3.5. And you square that. And that will be our new resistance. which is equal to 0.41 ohm. Let me just calculate that. 0.015 times 8 divided by 3.5 squared. I think it's not 0.41. I see there's a mistake in the area because the area is squared and we know that area is proportional to the square to diameter. So I forgot to square also this one. It should be squared so that this one should be raised to 4. So 2 squared. Squared, and that will be raised to 4. And if I double check that again, 0.015 multiplied by 8.015 times 8 divided by 3.5 raised to 4. So the answer is 0.409 or 0.41 ohms. So that's correct. It's 0.41 ohms. That's example number 3. Now let's go to example number 4. A steel wire has an initial diameter of 0.2 inches and a resistance of 0.75 ohms. After being drawn through a series of dies, its diameter is reduced to 0.09 inches. If the specific resistance of the material remains unchanged, calculate the new resistance, assuming that the volume remains constant. Again, it's similar problems from the previous examples. B1 is the same as V2, ρ1 is the same as ρ2, and we're given with the diameter and the resistance. So it's almost the same as the previous example. So we can use the formula again. R2 over R1 equals ρ2 V2 all over A2 squared divided by ρ1 V1 divided by A1 squared. And we can cancel out ρ2, V2. We have A1 squared divided by A2 squared. Then the diameters are given and also the resistance is given. The initial resistance is 0.75. So the new resistance now will be equal to 0.75 ohms multiplied by, don't forget to square this again, that's the area, and the diameter is given. The initial diameter is 0.2. 0.2, you divide that with 0.09. Then, instead of raising this one to square, we raise this one to fourth because the area is d squared. And you square the area, so you raise to the fourth your diameter. And if we check that again, so the answer is 18.29. Let me double check it. 0.75 times 0.2 divided by 0.09 raised to 4, and it's correct. The answer is 18.29 ohms. Next, a copper wire has a resistance of R. Another copper wire identical to the first but the 3 times the diameter is also considered. Calculate the resistance of the second wire in terms of R, assuming the material and length of both remains the same or identical. So identical, we have identical materials. It's the same copper, but they only differ in the diameter. The diameter of the second one is 3 times the diameter of the first, and all others are the same. All others are identical. What will be the new resistance of that wire? So all others are identical except the diameter. The diameter D2 is equal to 3 times the original diameter. And ρ1 is equal to ρ2. Length is equal to L2. But of course, because the diameter increases, the area will not be the same. Then the problem asks for the new resistance. So in this example, there's no volume indicated in the problem. So we'll be using L1 equals L2. It's the constant term. The length is the same. It's identical. So now, if you solve for the new resistance R2, you divide it with R1, which is R1 is equal to just, let me just call this one R, will be equal to rho 2, then L2 divided by the area, rho 1, L1 all over area 1. Then we can cancel out rho 2 and rho 1. It's the same copper and also the same length. So this will be A1 all over A2. Now if you look at this, the area is not squared because the length is constant in this case. While in the other problem, in the previous problem, this term is squared because we look at the volume as constant and it doesn't change. So be careful in using the same formula again. So here we don't need to raise that to the fourth. Instead, we raise that to squared only. So this will be d1 all over d2 squared, not to the fourth because the area is not squared, because we use constant length instead of constant volume. And we know that d2 is 3 times that of d1. So this will become d1 divided by 3 times of d1. Then you square that again, we can cancel out d1. So we have 1 over 3 squared, that's 1 over 9. So therefore, R2 will be equal to 1 over 9 of R. So the new resistance will be a ninth of the original resistance if the diameter is 3 times, increased to 3 times its original diameter. Next, a copper wire has a resistance of 22 ohms and a length of 700 meters. To reduce its resistance to 15 ohms, how much length must be cut off from the wire? Assume that the resistivity of the wire remains unchanged. So we have a copper wire that is this long. It's 700 meters long, and the resistance originally was, so R1, 22 ohms. If this is a 700 meter of that copper wire. Now, the problem asks for the problem wants to change the resistance and make it a 15 ohm resistance. But to do that, we don't need the problem doesn't include drawing the wire, meaning changing the area, but instead we cut some of the part of the wire so that the resistance will also decrease, because we know that length is proportional to the resistance. So what, and it is asking how much should we cut off, how much length should we cut off from the wire so that it will become a 15 ohm resistance. So if we cut this off in this, let's call this one, let's call it X for the wire that will be cutting off. So if this remains, this will be our new L. This is L1. That will be our new L2 if R2 is equal to 15 ohms. And because we're not drawing this wire, so we will assume that the area is the same area as the previous one. And it doesn't include volume, so that's true. And also, the resistivity is the same because it's the same wire, it's the same copper wire. So now, to solve for x, we just need to solve for L2 first. And after we solve for L2, because we know that the original length is 700, and if we solve for x, x will be just equal to 700 minus L2. So we do that. So first we solve for L2, so using R2 over R1, and the formula that we'll be using should be L over A, not anything that includes the volume. So rho 2 L2 all over area 2 divided by rho 1 L1 divided by area 1. And we can cancel this out. We can cancel out the area. And we know the values for the resistance. So this will become 5 or 15 divided by 22 because R2 is 15. And this will be L2 over L1. So L2 divided by L1, which is 700 meters. So that we can solve for the new length. The new length will be equal to 700 multiplied by 15 over 22. And this is equal to 477.27 meters. But this is not the unknown. The unknown is the length that we need to cut off. The length that we need to remove. So that's x. X will be equal to 700 minus 477.27. And if we subtract that, the answer will be 222.73 meters. The wire that must be cut off will be 222.73 meters in length. And it doesn't matter whether you cut it to the right or to the left as long as you remove 222.73 meters of the total length. Next, so this example is actually an example of the insulation resistance of cables. And the first thing that we'll be doing will be deriving the formula, and later on you can just use the formula if it's the same setup for solving the insulation resistance. So this is the insulation resistance. When we say insulation resistance, this is the cable. Inside the cable, this is the conductor. This is the copper wire or anything that is a conductor. And this conductor actually has insulation. So when we say insulation, it's the material that protects this conductor. That should be an insulator. Can be a plastic, can be a thermoplastic, and whatever. As long as this is an insulator. Now, if we want to solve for the resistance, insulation resistance, if you look at this case, if you remember in our previous discussion, if you're given a wire just like this one, this is the cross-sectional area, this is the length. The resistance of this wire is just rho L over A because we're measuring the resistance from here to here. And the area that we need to put in that formula should be the area that is perpendicular to the point where we are measuring, which is this area here. It's perpendicular to where we want to measure that. Now, in case of an insulation, we are measuring the insulation from here to here. Use another color. From here, oops. to here. Or it can also be the same here and here, because we are measuring the insulation cable. So if you look at the current that the resistance is resisting, it is coming from the conductor inside the cable, and it going outward when you touch the cable. If the resistance is low and you try to hold that wire, then there's a chance that there will be a current flowing through the insulation towards you. So to minimize that, we need to increase that resistance, and that's the resistance that we call insulation resistance. So now if we look at that orientation, if we apply again that formula, it's still applicable. R is equal to rho L over area. What will be the L and what will be the area? So the orientation will be changed because we're solving for the resistance of the insulation, not the conductor. Remember, not the conductor. So if we try to cut that, if we cut the insulation and make it a thin sheet, let's assume this is our insulation and make it just straight. And remember, this is the thickness, which is the same as this. From here to here, this is the thickness of that insulation. So now, where we are measuring at this point and this point. So what length we'll be using? So remember the orientation, the first one, this is the area, and this is the length. And if we want to solve for rho equals L over A, R equals rho L over A, this is the length and this is the area, and we are measuring here. Now, we are measuring at this point here, at the top and the bottom of the insulator. So our length will be the distance between the point where we are measuring, and that distance is actually the thickness of the insulation. So our new L will be just the thickness. And the area, if I draw this again, if we expand, this is the insulation, this will be the top, and the area should be the area that is perpendicular to where we are measuring, and that area is this area at the top. And how do we solve this area? This length here is the length of the cable. Let's call it L. This is the length of the cable, or yeah, not the length in the formula resistance. Rho L over A. And it's just a rectangle, but we need to know what is this length from here to here. And that length is we just expand, or we just cut the insulator, and that is just the circumference of the cable. Although if you want to be exact, if we cut that, the circumference, we have two different radius, the inside radius and the outside radius, or diameter. So this will be the question: what radius are we using to solve for this circumference? And just like what we did in our previous example, to be precise, we'll be using calculus to do that, and we will take the limit from the inside radius or diameter up to the outside diameter, so that the resistance will be more accurate than just taking the average or just choosing one radius, the inside radius. Okay, so we just call it R. So if we look at again the conductor here, this is the insulator, so this will be our RO, or initial, or inside, let's call it RI, or inside radius or diameter, and this will be our outside radius. So when we solve for the circumference, what we did from our previous example is we get a very small strip here. It's a very small strip, and that very small strip, we solve for the resistance of that because it's very small. The thickness of this one, we can just call it dt or dr, because this is with respect to r. Dr, then the resistance of that will also be an infinitesimal resistance dr. And we did this last derivation, and if we do that, that resistance will be equal to rho. Then our length will be that dr, because it's changing from ro to ri, so we don't know that. That's, to be precise, let's just call it dr. Then we divide that with the area, which is the circumference, the area, which is the circumference, 2 pi r, and we will just multiply it with the length of the cable, length times width. That's the area. So if we include this in our formula, this will be rho dr divided by 2 pi r l. And we don't need to use the conductance here, unlike in our previous example, because our dr is in the denominator. We did use the conductance to put it in the numerator, but in this case, we don't need to do that because the differential is now in the numerator. You can just directly take the integral. So r will be, we have a constant rho. It's the resistivity of the insulator, and the length is also constant, and we can just remove that 2 pi l, and we can just retain dr all over r. And our limit will be from the inside radius to outside radius. And if you take the integral of dr over r, that's the integral of 1 over x. Integral of 1 over x is just ln x. So r now will be just equal to rho over 2 pi l multiplied by ln of r. But if we apply the upper limit and the lower limit, the fundamental theorem of calculus, the answer will be ln of r out minus ln of r in. But one property of logarithm, if you subtract two ln's, we can just make it a division. So instead of subtracting, we can just divide r out and r in. And this is a formula for the insulation resistance. And we can apply this formula in this problem because we're given the resistivity, we're given the length, and we're also given the inside diameter and the outside, and the thickness is given. But if we solve for the outside, we just add 0.3. So okay, so our r in will be, the diameter is 0.25, so divide that with 2. So r in will be 0.125 inches. And r out will be equal to that 0.125, and we add the thickness, which is also given 0.3 inches, and that will be 0.425. And all given, we have the resistance and the resistivity. The resistivity is just 1 times 10 raised to 14. One times 10 raised to 14. Then you divide it by 2 pi. The length is, be careful of this. The length is 1,500 feet, and our resistivity is ohm centimeter. So we need to convert that feet into centimeters so that we can cancel out the centimeter in the numerator. Unlike the radius, we can retain that because we'll be dividing RO and RI. That inches or that unit will also cancel out. But in this case, in 2 pi L, that length will be dividing that with rho. So we need to convert that 1,500 feet into centimeter. And to do that, we have a conversion from centimeter to inches. I forget the conversion. We can just multiply that by 12 and that will become inches. And after multiplying by 12, 1 inch is equivalent to 2.54 centimeter. So 12 inches for 1 foot. Multiply this, then 1 inch is equivalent to 2.54 centimeter. So that if we cancel out that feet and inches, then we have centimeter in the numerator and also centimeter in the denominator. Then you multiply this with ln of R out, which is 0.425 divided by ln 0.125. I don't think the answer is correct here. You can just check it. As long as you follow this step and this formula, your answer should be also correct. Okay? Next. Here, it's the same thing. We can just directly use the formula. R equals rho over 2 pi L. Rho is 3 times 10 raised to 14. Again, this is ohm centimeter. So the length should be, we're finding per meter of its length. So 1 meter, so the length will be, L will be equal to 100 centimeter because there is 100 centimeter in 1 meter. Then 2 pi times 100. So that it will cancel out. Then you multiply that with ln of the diameter is 0.6 of the conductor and the insulation thickness is 0.15. So we divide it by 2, 0.15 plus 0.3. 0.3 plus 0.15. That's R in plus R plus the thickness. So that will be our R out. And you divide it by the R in, which is 0.3. And if you do that, it should be equal to this one, 1.94 times 10 to 11. But you can still double check the answer. I don't think these answers are correct. Next. Cable with a diameter of 3 cm and insulation thickness 1.5 cm has an insulation resistance of 800 times 10 raised to 6 ohm per kilometer. If the insulation thickness is increased to 2.5 cm, determine the new insulation of the cable. So we're talking about the insulation resistance per kilometer. So we can just use that and remove the L in the formula so that the answer will be per kilometer. And also, we can use the formula that R out is just equal to R in plus the thickness. Remember, R out is just equal to R in plus whatever the thickness of the insulation is. And in our case, the insulation increases from the original, which is T1. The original thickness is 1.5 centimeter, and we increase that into a new thickness which is equal to 2.5 centimeters. So it increased by 1 centimeter. What will happen to the resistance of the insulation? So we're just like telling we increase the length of our resistance here. So we can understand that the resistance will also be increasing because we know that length is proportional to the resistance. So using our formula R, rho over 2 pi L, ln of R out divided by R in. And we can divide R2 and R1 just like we are doing in the previous example, R2 divided by R1, where R1 is the original resistance and R2 is the new resistance. And again, rho and rho will cancel out. This term will cancel out. We can just put it to K. I can just cancel them all out, and I'll be just doing ln of RO over R in of the final divided by ln of RO over R in of the initial one. So the initial one is just RO over R in, or RO is just equal to R in plus the thickness, R in plus, let's call it T1 divided by R in. That's the initial one. And after for the new one, the R in still the same, but the thickness will be T2. The R in still the same, but the thickness will be T2. And given, so we know that R in is the diameter of the cable. So we just divide that into 2 so that we have the radius, that's 1.5. So ln of 1.5 plus, instead of 1.5, we add 2.5 because that's the new thickness, and you divide that with still 1.5. And divide the whole term to ln 1.5, that's the inside radius, and instead of 2.5 we add it with 1.5 because that's T1, and divide by 1.5. And if you know R1 is 800 times 10 raised to 6. 800 times 10 raised to 6. And if we divide that, let me just calculate that, ln of 1.5 plus 2.5 divided by 1.5. And divide that with the ln of 3 divided by 1.5. And that will be times 1.415. So R2 now, the new resistance now will be this one times 800 to the 6. And the answer will be 1,000, or you can just multiply it by 800 times 1.415, 1.415, 1132, 1132 times 10 to the 6 ohm per kilometer. And if you look at the answer here, this is 1008 times 10 raised to 6 per kilometer. And I think this is the wrong answer. And this will be the correct answer. I calculated it again, and the answer is 1132 times 10 raised to 6. And that's it. That's our examples for the resistances in the concept of resistance using those physical characteristics, or the learning outcome number 1. And we'll be doing for the second one, learning outcome number 2, we'll be again talking about resistance, but this time we'll be with the variation of the temperature. In all these examples, this calculation, we assumed that the temperature is constant and they are at constant value of 20 degrees Celsius. It depends on the given resistivity. So here are some exercises that you can answer. I can just browse down these exercises. You can just screenshot them and answer them on your own. Okay, that's it.